All right, hey class, this is Mr. Chase, and I'm gonna share our lesson today with you by video. So thanks for sticking with me, and you're welcome to watch this just on your own and pause, fast forward, however you like to go through this. Um, I think I'll maybe do it in two videos, one on 7.4, do the warm up and like 7.4, and then we're also going to cover 7.5 today too. 7.4 is like a shorter lesson, more kind of theoretical. And then 7.5 is like actually us finally getting to solve systems of differential equations. So that'll be exciting. All right, so let's get into it here. Why don't you pause and take a second to do the community builder with someone nearby, and you can work on the warm up together as well. And we'll come back together in a second. Oops, sorry. All right. Hopefully you've had a chance to do that. And in the warm up, you may have run into some trouble. So let me see if I can't. How do I? There we go. There we go. Okay, I'm going to do it over here. And I'll do it with you, and we'll see if we can't find the eigenvalues and eigenvectors of this matrix. Keep in mind that what we're trying to do here is solve this system, 1 minus lambda, 1 minus lambda here, and 1 minus lambda here. x1, x2, x3 equals 0, 0, 0. All right. And so as we go to find the eigenvalues, you know that what that means is what we need is the determinant of this matrix. We're going to like force that to be 0. So here we go. I'm going to do this times the determinant of this first. So that's 1 minus lambda times 1 minus lambda squared minus 1. And now minus this times the determinant of that. So that's 1 minus lambda minus 1 plus this times the determinant of that. So that'll be 1 times 1 minus 1 minus lambda. Yeah? And we're going to set all that equal to 0. So we'll do a little cleanup here. That's 1 minus lambda cubed. I don't know if this is the best way to do this. 1 minus lambda. If I see what I'm doing here is like distributing this to this and this, and so on. So then minus 1 minus lambda plus 1 plus 1, 1 minus lambda. I don't know if that's actually going to benefit me at all to have kind of grouped things in this way. Actually, I don't know that it did. Okay, whatever, but we'll just expand this out. So that's 1 using binomial expansion minus 3 lambda plus 3 lambda squared minus lambda cubed minus 3 plus 3 lambda plus 2. Oh, and as I'm even writing this, I'm noticing that like this 1 and 2 cancel out with that negative 3. And that negative 3 lambda cancels out with that 3 lambda, so that we get just simply um, uh, negative lambda cubed plus 3 lambda squared equals 0, which factors nicely as that. And the eigenvalues and eigenvectors are now apparent. We'll call eigenvalues, excuse me, are apparent. We'll call lambda 1 3 and lambda 2, and I guess like lambda 3 as well. It's like a repeated eigenvalue of 0. So interesting. This warm up is like causing us to think about this in new ways. We've got a 3 by 3 system, which is throwing a wrench into the works, and we also have a repeated eigenvalue to think about. So might be an opportunity to discuss that. So let's start with 3 and see what that does for us. So we'll go back to that original system, putting 3 in where it belongs. So that'll end up being a negative 2 here on the diagonal in all of those spots. X1, x2, x3. And now, when we were doing 2 by 2 systems, there was some redundancy, like one row was just exactly redundant with the other, just like a scalar multiple. Here it's not too bad. Okay, we're gonna have to do a little row reduction, but it's a little less obvious like where the redundancy lies. So I'm gonna do, we'll call this, I know you guys don't love row operations, but someday you'll get used to them. You'll love them, I promise. Okay, let's call those row 1, row 2, and row 3 again. I will do nothing to the first row. And the second row, what I'll do is I'll do row 1 plus 2 R2, 2 copies of R2, row 2, so that this will cancel out here. So I'm going to multiply this entire row by 2 and add it to the first row. So 2 times 1 is 2, plus negative 2 is 0. That's why I did it. 2 times negative 2 is negative 4, plus 1 is negative 3. 2 times 1 is 2, plus 1 is 3. And I'm going to basically do the exact same thing with row 1 plus 2 times row 3 to get the second, to get the next row too, so that we get 0 here. We'll get a 3 and a negative 3. So you can already see kind of some of that redundancy that is appearing here. Okay, so now as we go to rewrite this system, I'm going to do maybe one more row operation here. I might divide through by negative 3 here. And you can see that the third row kind of just is a scalar multiple of the second row. And so as we add it, if we take the current row 2 and add it to row 3 and replace that into the row 3 position, we just get 0, 0, 0. So now we have the reduced system here, and so that's the new system. There we go. All right, so now what does that actually say? Let's try to unpack that. What it says is negative 2 x1 plus x2 plus x3 equals 0. And it also says that x2 minus x3 equals 0. Or, said another way, x2 equals x3. Okay, so let's choose x3 to be, it's our free choice like we've been doing when we're doing eigenvectors. X3, let that be 1. That forces x2 to be 1. And that forces, notice that forces, if you go back and put 1 and 1 in for those here, that will force x1 to be also 1. All right, so what does that mean? It means that our eigenvector that goes along with the eigenvalue is 1, 1, 1. All right, good. So we found an eigenvalue-eigenvector pair. And now let's do it with the other one, this repeated eigenvalue. So I'll do it over here. Eigenvalue 2, or I guess we call it 3 as well. And now notice, actually, this one might actually be the easier thing, because take a look at when we do 1 minus 0 on all this diagonal, we actually just get that 1, 1, 1, 1, 1 matrix again. 1, 1, 1, 1, 1, 1, 1, 1, 1, x1, x2, x3 equals 0, 0, 0. Beautiful. And actually, the reason this is a little bit easier is because we just get one equation from all of this. If you write out the other rows, they're obviously the same. So now, so the matrix system is not the hard part. The next part is maybe the part that's you have to kind of think hard about interpreting. Like, okay, so what do we have here? Seems like we have like a lot of freedom, and in fact, we do. We have kind of 2 degrees of freedom, so we can actually pick freely x1 and x2. So let's let x1 be 1 and x2 be 2, and that forces x3 to be negative 1. And that might seem like somewhat arbitrary, but you're thinking, really? Can you really just do that? And the answer is yes. And are there other ways to do this? Will you get other eigenvectors? And the answer is yes. Oops, sorry. Let's let x1 be 0 and x2 be 1. And if we do that, then we get x cubed equals negative 1. Okay, so I am, I guess, proposing that with these, we take these to be the other eigenvectors. Excuse me, There we go. X2 and X3 are going to be those. Now, okay, so we've done it. We're going to say that we're done with the warm up, but I'm going to just provide one additional small amount of commentary because I know a lot of people are like, wait a second, why didn't you pick? You could have picked. You could have picked all kinds of things in this last moment here to get those two vectors. I'm just putting a box around right now, and you're absolutely right. We could have picked lots of other things, and so those are not like unique eigenvectors. And so just to illustrate that idea, let me do like kind of a little bit of a thought bubble here and take you back to a thought that we had very early on in your study of vectors. So here we go. Back in the day, when you were first discussing like I and J notation, you understood that it wasn't just like a notation. It was uh, it was a way of building every vector in the world from those two vectors. So you have I and J, and they're not just like notation. Those are vectors. And the idea here is, of course, that like, let's say you have the vector 5, 3. Well, it can be built from I and J. You almost don't even think about it being building a vector from another vector, right? But that's what it is. It's like you just formed a linear combination of I and J. And so there's this kind of deeper thing that we're saying. We're saying that like I and J can build every other vector in the entire plane, right? But maybe we didn't stop to appreciate the fact that there's nothing special about I and J. Well, there is. They're orthogonal, so we like that. They're like convenient, right? They're convenient, but they're not the only ones that can form every other vector from them. Like, say we take these two vectors. That's not going to do it for us. There we go. How about that? All right, these two vectors are, let's say, I equals the normal I. But then we take this other vector, let's call it U, 1, 1. And could you form every other vector in the plane from these two vectors? True, from like U, from I and U. Like, is there some number here and here you could put? Figure it out. I bet you can do it. I bet you can figure it out. And the answer is yes. The answer is yes. And there's nothing special about the vector 5, 3. Any vector in the entire two-dimensional plane can be built from these vectors, I and U. Oh my goodness. Shocking, right? Well, and the thing you need is just two vectors that are linearly independent. And then you can build every other vector in the plane from those two. It's just I and J happen to be like a really convenient basis. And that's what it's called. They're called like a basis. And the technical term, instead of calling like build, saying we build every other vector in the plane, we say that I and J or I and U span the plane. Like they can get they can get to any other place in the plane kind of through a linear combination of those two things. And the same kind of phenomenon has happened here too. Like um, these two vectors define like a plane, and are there other vectors that would do the job? The answer is yes, right? Like they would also span the plane. We just picked two convenient ones. So um, if you pick another one here, it will be some linear combination of the other two, right? I mean, you understand this is a plane, and so I don't know. It also reminds me of way back in the day when we were doing planes, and actually sometimes we did that. We were like, find the equation of a plane containing these two vectors and a point, right? And obviously those would not be the only two vectors that you could have used. There would have been lots of other vectors available as well. So I don't know if that kind of clears up the theory there. I know that's a little weird, but hopefully you're okay with understanding that someone nearby might have like a different set of vectors here. It's like as if they had chosen this versus this, right? They both do work, I promise. So that's a little weird, but we'll leave it at that. Okay, so there's the a very thorough discussion of the warm up. I hope that was good. Did you also think about what you would like to have a robot do for you? Maybe like maybe your answer is this. All right, let's get into our lesson here today. Like I said, in this first video, we're going to talk about 7.4, and then we'd like to talk about 7.5 as well. I thought I'd just split it up to make it two separate videos to make it kind of more I don't know, digestible. 7.4 is basic theory of first order linear equations. So, like I said, we're going to throw a bunch of theorems at you that allow us to then kind of get into section 7.5. But I think in the homework, like, I didn't assign any problems from 7.4. It's very theory heavy, and I'm trying to keep things fairly practical in the course. So, really, we're just going to use 7.4 as a stepping stone to get to 7.5. All right, so in general, a system can be written this way. I think you would agree. And but we can also write it in a more compact form where the red, blue, and green are kind of summarized into these vectors. This shows off kind of the power of linear algebra to kind of make things prettier. And it's not just prettier, it also kind of helps us understand that the things that we're going to be doing and discussing in this 7.4 section and 7.5 and everything else we're doing, all of it is like really actually quite analogous to what we did in chapters 1 through 4 with scalar equations. If they weren't bold and like not italicized, it would almost look like a scalar equation, right? It's very, some of these things look very familiar, even though we're in vector world. Just take a moment to understand too that like, yeah, this here is a matrix of coefficient functions, p functions, in a square matrix, n by n square matrix times a vector x1, x2, x3, etc. Right? That's what this is, right? All right. So speaking of things that are analogous with things we did earlier in the year, the principle of superposition is one that you've heard of before, back in the earlier chapters in those contexts. Well, the same is true here. If you have, uh, oh, by the way, I didn't mention, we're going to leave for later a discussion of non-homogeneous systems, and we're going to just try and build up a theory of just homogeneous systems right now. We'll get to non-homogeneous systems, but like we did the theory that way earlier when we were doing differential equation, or earlier when we were doing second or third order differential equations, we kind of focused on homogeneous equations first. So this is kind of right. We got to do things in the right order. All right. So, and the thing you'll remember about those is that, like, so if we have a solution x1, some vector, uh, excuse me, let me use the right notation. X1, let's say that is something that solves this, makes this equation true. But we have another one that also makes this true. Like they both work. Yay. Well, then, this is not going to be a huge surprise to you, then the linear combination of those will also be a solution, right? It's like very, like I said, very similar to what we said earlier in the year with scalar equations. In fact, we also have the appearance now of the Wronskian. And the Wronskian is going to be that thing that is the determinant of this matrix X, capital X. We're calling it capital X. And it's the matrix whose, like it says here, the matrix whose columns, each column is those solution vectors, right? Oops, excuse me. So let's see here. Uh, right, this is like x1, x2, this is xn, right? Each of these columns is a vector. And so we can take its determinant, and that's called the Wronskian. The theorem 742, again, copied and pasted from your book. Did you notice, by the way, you don't need to take notes on these slides. These are just popcorn slides, right? Just let this wash over you. These all appear exactly the same way as they appear in the book. So I just want to kind of highlight, give my 2 cents on them, and then really just trying to get to 7.5 here, right? That's the thing we really want to talk about is 7.5. So the idea of taking linearly independent solutions, if you have linearly independent solutions of a system of order n, then the general solution can be written as the superposition or like a linear combination of all of these, where C1 through Cn are like to be determined. So this is called the general solution, and that language is just paralleling the language we've been using all semester in differential equations. And same with the fundamental set of solutions, that term we've used before as well. And the fundamental set of solutions are these x1, x2, xn, right? Those linearly independent solutions. Those are called the fundamental solution, right? If they are indeed linearly independent. Great. Okay. So again, just some theory. Last slide of theorems, I promise here. The Wronskian, this top theorem here is like us relating the last two ideas, the Wronskian and this idea of linear independence. But of course, this is not a shock to you that linearly independent solutions have a Wronskian that is uh, non-zero, right? So all you have to do is, because these are functions, um, t could be any number in between, whatever and whatever. And so uh, you're going to get like a different Wronskian value evaluated at all of those different places inside this interval. And so this theorem just helps us understand that we actually have to just check one of some convenient point in there and make sure it's not zero. Okay, last theorem, and this really sets the stage for like a little bit later, but this is just like it says here, a very convenient set of initial conditions that yield a very convenient fundamental set of solutions. So notice these column vectors have a very nice form. They're column vectors where the position 1 has a 1 in it here, or position 2 has a 1 in it, or position n has a 1 in it, and everything else is 0 in these columns. So you can imagine those are like, okay, those are good initial conditions. And by initial conditions, what we mean is like if you plug 0 in to your solution vector, or whatever your start value of t is, t0, it is most often 0, then the thing you'll get is if you plug 0 in for t in the first vector, you'll get this vector, right? That's the like initial condition for that, and so on down the line. If you plug in for x2, you'll get this, etc. So these are the initial conditions. These are the initial conditions. Sorry, I'm drawing all over the place. And if that's true, then these form a fundamental set of solutions. Um, and so, yeah, I don't know. I guess I should just say it's like a very convenient fundamental set of solutions, for reasons that you'll see in a future section. It's just like very convenient. These are just very convenient initial conditions, um, that will make our math quite a bit easier later. So it's just worth mentioning right now that that's a nice set of initial conditions. I guess that's all I'll say for now. Okay. To summarize, we're trying to make 7-4 as quick as possible here. This is our last 7-4 slide. You didn't have to write down all that necessarily that we just did, but you might write this down, right? These are the kind of big picture summary of what we just talked about in the last slides. First, if you have a set of n linearly independent solutions, x1, x2, x3, etc., to the system, the homogeneous system, then the linear independence implies a non-zero Wronskian, and also implies that we have a fundamental set of solutions, right? That like we've got them all. And this is the last point here. Under some very mild conditions given in this section, these kinds of fundamental sets of solutions always exist, and they can be represented as, like we just saw, a linear combination of those fundamental solutions. Okay, so pause there. I'm going to end this video here, and then really, my goal is to kind of cover 7-4 and 7-5 in one day. We'll see. So 7-4, there's the end of that video, and so be sure to jump into the next one, 7-5. Thanks for being so diligent to follow along.